Okay, sigma notation. Our goal here is basically to present a systematic way to talk about sums of numbers. And to give you an example, consider the sum of the first n natural numbers. You may know this fact, that if you add all the numbers from 1 to n, the total is n times n plus 1 over 2. Right? And so what this statement means is, if I stop adding at the number 5, for example, that means I'll take n equals 5, and this sum is going to be equal to 5 times 5 plus 1 over 2, which is 30 divided by 2, or 15, which is the same thing that you would get if you add 1 to 5 manually. Right? So that's what this statement means. It's true for any n in the naturals. So what we'd like to do here is basically to make writing this entire sum on the left-hand side easier. Right? So instead of writing ... here until n, what if we could just write this as a single term? Right? And so I'll show you what this looks like in sigma notation, and then let's go through its parts. Okay, so this is the Greek letter sigma, which stands for sum in this case. And what this notation here is telling us is, take all integers from I equals 1 to n, one by one, plug them into this term you see on the right, which is just I, and add them all up. Which means what you'll get here is exactly that sum above. When you plug in I equals 1, well, I equals 1, so it's just a term 1. When I equals 2, that's the next term. When I equals 3, that's the next term. And you keep going until you reach n. And note here that it is implicit that we are incrementing by 1 at each step. So you don't go I equals 1 and then 3 and then 5, right? So we can't skip numbers. You have to go up by 1 each time. And I should mention that this is called the index of the sum. Right? And so in general, what this looks like is the following. The notation sigma, or sum, from I equals 1 to n of ai simply means, again, just start from the number 1, plug it into a sub I, so that's a sub 1, whatever that is, then take the next integer up, a sub 2, when you plug in I equals 2, and again so on until you plug in n minus 1 and then n. And these numbers could mean anything, right? It's a sequence of numbers from a1 to an. Usually what we'll be looking at are sequences where we know a formula for each term. So for instance, in the previous page, it was a sub I equals I, right, which is also down here, which means the ith term of the sequence is simply I. Right? Now I can have another example. What if I took ai equals I squared? Well, now if I wrote this sigma notation here, sum from I equals 1 to n of ai is the sum from I equals 1 to n of I squared. And now when I plug in the numbers from 1 to n, it's now 1 squared plus 2 squared plus 3 squared, and so on. right? So really, it's just shorthand, right? The sigma notation is just a more convenient way to write this long sum of terms. Now let's just go through some properties quickly here. Some of these will seem pretty obvious to you, like the first one. The sum of C from I equals 1 to n. Okay, so what does this mean? Note here that C does not depend on the index I. And so what that means is when we're plugging in the number 1, the number 2, the number 3, all the way to n, this term here, C, does not change. And so when I equals 1, it looks like this, it's C. When I equals 2, well, it's still C. When I equals 3, it's still C, and so on. And for I equals n, it's still C. And so we know exactly what this adds up to. You're adding n copies of C together, which means this is just n times C. Right? And so this will be a useful property. Right? If the term inside does not depend on I, you're just adding up n copies of the same thing. And in fact, we can extend this to the next property here, which is, what if there was a factor? And let me just encircle the C here. What if there was a factor C that does not depend on I inside the term here, inside the summation? Then what will happen here is, again, the same thing. Let's take 1, plug it in. Well, now it's C times A1, right? AI depends on what I is. The term that's next is C times A2. So on until C times AN. All the terms have a C in them, so that means we can factor out the C. And just leave ourselves with the sum from A1 to AN on the right. Therefore, this is just going back to our sigma notation. C times the sum from I equals 1 to n of AI. Right, so it's the same idea. Whenever you have something that does not depend on I, you can basically take it out of the summation, factor it out of the whole sum. Now I have two other properties here on the right. If you have the sum of terms that are themselves sums or differences, well, it turns out you can break out the summation into two individual summations. One for AI and one for BI. And finally, the last property here is, well, it doesn't look like anything yet, right? But what I really want to say here is, whenever you have a summation from I equals 1 to n, well, remember, that's just a long sum of numbers. So you can cut the sum anywhere you'd like. Say you can cut it earlier at some integer m, and continue adding terms from m plus 1 to n. Right? And so really, just to point this out here, sums don't have to start at 1. Right? And so this will be helpful for us down the road once we get into integral calculus and sequences and series. Finally, here are two other properties that you may find useful. If we change I to I squared or I cubed in our sigma notation, then we also know exactly what the totals are when you add up to the nth term. Okay, so you'll see them in use later on. I just want to end this video by giving you a concrete example of where we can use sigma notation. And here's an example where we're asked to basically write the sum of the areas of all the rectangles in this figure using sigma notation, given that the function that's drawn here is the function x squared over 2 plus 1. Right, so rectangles. Right, how do you get the area of a rectangle? Again, it's just length times the width or the height. Right, it just multiplies dimensions. And so in fact, we can actually compute the area of each rectangle individually. Right, so what's the area of this rectangle on the right? Well, the width is 1. The height is, well, we don't know it, but we can know it by just plugging in 4 into your function, right? Because the top right corner of your rectangle is exactly on this curve of f of x. So when you plug in 4, it's 4 squared over 2 plus 1, and that's 16 divided by 2 plus 1, which is 9. So the area of this rectangle is 9. And we can do it for the others too, compute them one after the other. But we want to use sigma notation here because we want to see how we can express the sum as just a single term. And so instead we ask the question, for each I, what does the ith rectangle look like? Right? Because we eventually want a sum that looks like this. And again, remember that we don't need to let I start from 1. In fact, I can let I start at 0 here. Right? Consider the first rectangle to be the 0th rectangle. The next one to be the first, and then I equals 2, I equals 3, and then I equals 4. And so now the question is, and I'll write this down on the right so we have more space. Sum AI from I equals 0 to 4. What does AI look like? So if AI is the area of each rectangle, right, so the ith rectangle has what area? Well, the width is constant, right? Each of these rectangles has width 1. The width is 1. What's the height? Well, if you notice what's happening here, the height is determined by the function value at each of these points, right? Which is the point on the right of the rectangle. So for the 0th rectangle, it's the function value at 0. For the first rectangle, it's the function value at 1, and so on. And so I could just write here, well, it's whatever the function value is at I, right? And this would be the answer. Really, we're just adding up f of I, plugging in I equals 0, 1, 2, 3, and 4. And we can also write this using the actual formula for f of I. Okay. So let me just end by giving you a question here. I changed the rectangles here a little bit, right? So instead of just having 5 rectangles, now we have 10 rectangles. And I'd like you to think about the same question. How would you write the sum of the areas of all these rectangles as a single term using sigma notation? Okay, so again, think about what I has to be, right? What range of numbers I will take on, and what does each term look like, right? What is the area of each rectangle as it depends on I?